Okay, great. Thanks everyone for joining us today. We will have our monthly webinar. Today, Nan Zhang is here to speak with us. She's with the University of Stavanger. Nan, please take it away.
Okay. Thank you for having me. So as Lisa already said, my name is Nan Zhang, and I'm a researcher at the University of Stavanger. Today I'm going to talk about federated computation. And in this presentation, we will go through the basics of this technology, and also we will show a case study of this federated learning on a real field case study. And we will also explore the potential of using this technology in cross-domain knowledge discovery and utilization, so that we release the full potential of the digital subsurface. So let's dive into that. So we know that on this map, we know there are many companies. As of the 2020, at the end of the 2020, there are actually 29 operational companies that are doing explorations and productions around our Norwegian continental shelf. And each, they own their own lessons and doing operations on their divided regions. But we know at the subsurface, actually they are connected. So it gives us a potential for collaboration. So we can, if we can accumulate, we can access to multi-site data, we can then derive the high quality decisions and mitigating operational risks. And how should we achieve that? And we will use the technology we called federated computation. And why we see the key is actually to access to multi-site data is because of this knowledge pyramid. We see that the data is actually sitting on the bottom of this knowledge pyramid. So it makes that the quality of the wisdom or the quality of our decision made is actually based on the amount of data we have accumulated. If we can access to the multi-site data, we are actually expand the volume and also the diversity of this data. So it represents or it reflects a real distribution of our reservoir geometries and also the characteristic of our reservoirs. So based on that, we can have a more comprehensive information about our subsurface, and then we can gain more generalized knowledge. Or from that, we can even derive new knowledges. And based on that, we will have a better chance to make very good decisions and reduce the risks made by these decisions. And for the subsurface digital transformations, the current status is actually they're developing quite rapidly. And for example, the very large big service companies like SLB and Halliburton, they all embrace the open source standard-based data format called OSDU. So why they use this format is actually to eliminate the data silos, to actually the joint forces across different organizations to solve same set of problems that have the common interests. But actually, the full potential of utilize this OSDU data format is still uncovered. It's not fully released yet. Why? Because recently or currently, we still use the centralized platforms. So what it does, so it actually consolidates your data on a private cloud. That is very secure, very good, and very easy to streamline applications around your private cloud. But it still sets boundaries for cross-organization collaboration. For example, if we have two different organizations, one is SLB and one is Halliburton, and one is Aker BP and one is Equinor. If they want to have a common set of problem, and they need to train a machine learning model and accessing to different data owned by each client. How they need to, and they need to actually transfer or move their data to a centralized location. So if that is what they need for a collaboration project, we know that moving the data is very, very expensive, and also you're also concerned about your data privacy, and you're also concerned about your digital. This is a very valuable digital assets, so you want to keep your ownership for your digital access. So it is not very convenient, or it is very challenge to have some to discover the cross-domain knowledge using the centralized approach. So how should we do that? We actually introduce this technology called federated computation. So what this means, so it is actually a decentralized computing algorithm. So what it does, it is coordinate across multiple decentralized devices and utilize multi-site data and models to complete a predefined workflow. So there are several keywords here. So actually we know that the data and models or the digital tools, they're located or they're owned by different clients, but altogether we can compute a predefined workflow. So the key for this federated computation is actually to move the computation to where the data is. So in this way, the data will always kept locally controlled by their owner, and the data will be processed locally. So by doing so, that we don't need to move the data. So we save a lot of latency, and we also save the power consumption of while we are collaborating on doing this federated computation. So in this way, it facilitates a secure and efficient cross-domain collaborations without compromising on data control or data privacy. So you may ask, how does it work? And today I will give you an example of using a federated learning. So the federated learning is a specific application of federated computation focused on machine learning. So they all share the same key features. As we go through that, you can see what are the key features of federated learning and federated computation. So how would we start? We will start with our initial model. So this initial model will initially located in the central server, and we will distribute this initial model to different clients. So maybe one client is one organization. You can see maybe this is UAS, and this is North, and this is Equinor, and this is Aker BP, for example. But we don't want to distribute our initial models to all the clients. Why? Because maybe not all the clients are available, and also not maybe all the available clients are suitable for our federated learning. We only want to choose the suitable clients that fit for our purposes. In the digital subsurface domain, maybe we just want to share this initial model with the clients that in our nearby fields, and we also share same interest in solving this problem. And after we identified the suitable clients, then we deploy this initial model to each of these clients. And on their own devices, they will use this initial model to access to the data and train a local model on these devices. And during this process, one thing we need to know is that this data always remain on your device, and it was never sent to another client or never sent to the central server. So only the locally trained model and the parameters in this model are shared by the others. So after all of our clients do this training, and we will aggregate the parameters of this locally trained model to the central server. So the parameters may include the weights and biases and other parameters of machine learning, and we will average them out using an aggregation algorithm and to create a new combined model together. So this new combined model will be used for the next run, will be used for the next run as the initial model for the next run of the training. So after several training steps, and your combined model will start to show signs of intelligence, and it becomes smarter and smarter. And eventually we can share this combined model with all our clients and discover the cross-domain knowledge and utilize it. So in summary, actually, the federated learning is a collaborative, decentralized machine learning algorithm. It enables all the collaborators to train smarter models altogether. And during this process, we reduce the power consumption and also preserves our users' privacy. And in our study, we use the federated learning to predict the drilling rate of penetration. So, and we use the data set from the well fields that provided by Equinor and to see if the federated learning can be utilized in the digital subsurface in a real field case study. So in this case study, we utilize the data sets from 5 different wells. And altogether, we trained a combined model using the federated learning and to predict the rate of penetration of a new well. And in order to show the benefits of this combined model, we also trained five different machine learning models using the data from individual wells. So we have 5 single well based machine learning models as the reference model, and we also altogether trained a combined model using the federated learning. So so how do we do that in order to be consistent in this comparison? So all those models we use this attention long short-term memory network. So they all share the same structure of the machine learning model, and all they aim to predict the next 10 future rate of penetration values using the last 100 historical data points. So how does the results look like? You can see that we have plotted this test accuracy versus the training epoch. And all those solid lines are the training accuracy of the reference models. And only these dashed lines is the training accuracy of our combined models. So based on this figure, we can see that there are very, very significant sign of overfitting phenomena for this single well-based machine learning models. So it means that when the training epoch actually increases, the test accuracy decreases. That is not what we desired. But on the contrast, we can see the performance of our combined model. It's reaching the highest test accuracy after the 100 epoch. And also it overcomes the phenomena of this overfitting problem and provides the highest generalizability across all data sets. So it is a very solid results that the federated learning can actually provide us with can actually enable us to get cross-domain knowledge. And this domain knowledge, if we use that, we can derive much better decisions. So we also know that discovering knowledge, we can use federated learning. But how about utilize those knowledge? So in the knowledge and the data, they may located in different different organizations. For example, in UAS, we have developed a very good machine learning model. But how should we share this model, or how do you as a company want to use this model? And we are sitting on different platforms, how to efficiently use this? So it's still a question mark. So therefore, in our NCS 2030 Center, one of our projects is actually to develop the Federated Knowledge Cloud. In this project, we aim to develop a cloud-based open source platform that provides the users with seamlessly access to data and tools located in different decentralized devices, and to execute the predefined workflows by using a federated computation algorithm. It means that we can move the computation or move the digital tools from one platform to another platform and do all the analyze here and provide you with the results that you need. In our research, we are focusing on both the theoretical development and also the application deployment, these two perspectives. So for example, we combine the federated computation with blockchain, and to ensure that our users, to all the users or all the clients, when they execute the workflow, they actually execute it in a transparent way. And also this workflow will be automatically deployed on your device. And so that will help the users to see the transparency, and also we will use the right tools and we will use the right data to do this federated computation. So you know that what you are doing and what data you are accessing and what tools you are accessing by using the blockchain. And another perspective that we combine the federated computation with the large language models. And by doing so, we develop a question and answer chatbot that on context is extracted from multiple resources. So how it does, we will I will show you a demo. So this is a video, I don't know, oh, here. Okay, so for example, we will ask a global question, and there are 3 organizations that we can access. And for when we ask a global question, those are 3 different clients, they will have their local questions, refined local question. And based on this refined local question, they will retrieve their information and provide with a local answer. After this local answer generated by each client, the global server will aggregate all those local answers together and give you a combined answer together. For example, in this demo, we ask who has the most population, and we can see that Norway and Sweden and Denmark have its own answers, and altogether we know that Sweden has the most population among those 3 countries. Another important aspect is that we know that large language models sometimes give us answers that are not true. How about in this case, if we ask a random question and ask our clients to solve this question? So which country has the most handsome people? So let's ask them. So all of our clients, they think and think and think. Okay, Norway is very honest. I don't know. And Denmark is very honest. I don't know. But Sweden, it seems like he wants to fool us. But altogether, our global answer would be able to identify. So this Sweden is not giving us the answers that we desired. So actually, this global answer would be able to provide us with a very with honest results. So in this way, we prevent the large language models to give us some made-up answers. So that is not the end of the story. So currently, we are focusing on this project called D at T, that is AI-powered data and tools integration. So in this project, we are focusing on combined large language models with a federated computation. So we know that large language models is very good at understanding the user's questions and identify or retrieval the information and also tools that need to solve this question. So by this process, we want the large language model to automatically define the federated computation workflow that we need to execute across different platforms to provide the in-depth data analysis to give the precise results in order to answer the user's questions. For example, if I ask a question about what is lithology of this well logs, so he will go and find the required document and also go to find the required tools across different platforms and execute this workflow on the flight to automatically execute this workflow. And based on this data analysis, and then we can get the results for our users. So it actually aims to orchestrating different digital access across different decentralized devices to align with our users' queries. So what it does, it's actually not only streamlines this process, but also significantly reduce the time and the expertise required to initiate and to manage this kind of workflows. And it truly helps the users to benefit from this platform. So it helps all the collaborators on these networks to be able to benefit from this collaborating initialization, to benefit from this collaborative activities. Okay, so here are some take-home messages that as a conclusion. And we know that federated computation offers a secure, decentralized computing model. It preserves privacy, and at the same time, it will help you seamlessly access to the multi-site data and multi-site tools to perform a comprehensive workflows. And by using the federated computation, we can discover cross-domain knowledge. And also by utilize the tools and data on different digital platforms, we can enhance the decision-making process. And by integrate the federated computation with blockchain and with large language models, we can simplify users' engagement with automated in-depth data analysis. And this data analysis will aims to answer the user's questions. And by doing so, this integration drives more efficient operations, foster collaborative innovations, and sharps the decision-making capabilities for all the clients that's willing to collaborate. And I think that is the presentation for today. And here are some publications that we made within 2 years. And some publications are still in processes. And if you're interested, we can send you the copy of those publications for further information. And thank you very much for having me. And if you have any questions, I will be glad to answer them.